The following video documents a new software simulation tool that models in 3D the beam pattern for phased arrays. Under construction in the laboratory is a design you see here, a phased array of 5 patch panels horizontally by 4 patch panel rows vertically. Each go back here. Each element is a patch antenna purchased from Elcom, model number HG2458-LP. This patch element is responsive in 2 bands, 2.4 to 2.5 gigahertz and 4.9 to 5.8 gigahertz, vertically polarized, lower band 9 dBi gain, upper band 11 dBi gain. Both were essentially 2 patch panels connected to a single end connector in the back, as you can see here. So this is the proposed design. I thought it would be nice to model the beam pattern before physical construction began, to see how the interspacing between the elements, in this case interspacing is lambda over 2, that's kind of a standard spacing for patch arrays, and the simulation tool will allow that interspacing to be varied. The restriction at this point on the first version of the software is that the panel be flat. In this case you can see that the construction was a spherical form to perhaps increase the beam sweep from side to side. So that's the proposed design. The video will be split into 2 separate videos because of limits in the record time. So the first video will show this array being built from isotropic point sources, up to 5 point sources vertically, and up to 4 and eventually 5 point source arrays. Okay, here's the radiation pattern for a single point source, 0 dBi in all directions. Okay, so I'm going to add a second point source horizontally, so we can have 2 point sources sitting horizontal to each other. You can see the typical donut shape that you see in a number of phased array text or antenna references. And I'm going to determine the width of the beam here. I'm going to point the array down so it can be better viewed. And by adding the second point source, I now have a power level of 3 dBi, so the 3 dB down beam width, like a 0 dB on each side, it's roughly an angle of 42 degrees from center, and same is true for the other side. Roughly 42 degrees is the half power beam width, so 42 each side. 82 degrees is the beam width with 2 isotropic point sources horizontally. So I'm going to add a third point source. And determine the beam width. Now up to 4.77 dBi. So the 3 dB beam width from side to side would be looking at 1.77 here. 25 degrees from center to side, and same is true for the other side. About 25 degrees. So the 3 dB down beam width with 3 isotropic point sources is 50 degrees. Add a fourth isotropic beam source horizontally. You can see the pattern here. Determining beam width. sure everything is perfectly straight. Okay, I'm now up to 6 dBi gain, and the beam width would be 18 degrees from center to side. Same is true for the other side. Roughly 3 dB, 18 degrees. So total 3 dB down beam width is 36 degrees. This is with 4 isotropic point sources horizontally. Here is 5 point sources. Just feel what that looks like there. And you're up to a roughly 7 dBi gain, and then 3 dB down beam width would be, to each side, 4 dB roughly there. Well, if I get it to respond here, 14 degrees from center to side. Same is true for the other side. Oops. Okay, 14 degrees, so 28 degree, 3 dB down beam width with 5 isotropic point sources. And just for grins, let me show you an end-fire configurations you see in a number of the phased array of text. If I can get things back to where they should be here. Turn it to the side. Okay, I have lambda over 2 spacing between each of the 5 horizontal elements. And if I set the horizontal beam steer angle at 90 degrees, you see the standard end-fire configuration that you see in a number of texts. Gives you a 3D view of that. Okay, so let's continue on here. I'm going to add one additional vertical row. So we now have 2 rows of isotropic point sources, with each row with 5 horizontal elements. Get an idea of what this looks like here. I'm going to point it down so we can, well, perhaps point the side would be best. Okay. We're up to 10 dBi. Again, this is 2 vertical rows with each row horizontally 5 point sources. 10 dBi, and so if we sweep to 7 dBi for the 3 dB down point, roughly 42 degrees on one side and 42 on the other. So we're seeing the similar performance as adding point sources horizontally. As you add them vertically, we're now 2 rows vertically, so our beam width is roughly 82 degrees. Going to add a 3rd row. So we have 3 rows, each row holding 5 isotropic point sources. Gain is 11.7 dBi. If we sweep the side to side on that, would be 8.7. Roughly 26 degrees to one side, and same is true on the other. .6 So with 3 vertical rows, our beam angle now is 50 degrees essentially. Same performance as adding point sources horizontally. So I'm going to add a 4th row, so 4 rows high, each row holding 5 horizontal isotropic point sources. Gain is roughly 13 dBi. So I sweep to 3 dB down point. Get it to cooperate here. 18 degrees from center to side. Same performance on the other side. 18 degrees. So with 4 rows, we have 36 degree 3 dB down beam width. And to show symmetry, I'm going to add a fifth row, even though our construction is 5 horizontal elements by 4 rows high. I'll go and show a 5th row here for symmetry. Zoom in a bit, and our gain is at 14 dBi, so sweeping each side to 3 dB down, 14 degrees, and 14 degrees to the other side. So with 5 elements, or 5 rows high, our 3D beam width is 28 degrees, and of course as you increase the number of elements horizontally and vertically, the beam width continues to decrease, become narrower and narrower and narrower. Okay, so this gives a picture of our design here. I'm going to rotate it around so you can see what this looks like. And I'm going to sweep over to, if I can get my markers to cooperate here. Here we go. Alright, looks like we have, this lobe is at 7 dBi. This lobe is essentially the same. And our main lobe is at 14. So side lobes roughly 7 dBi, main lobe 14. So we have a 7 dB dynamic range between the strongest lobe to the side lobe. Okay, let me reset everything now. The direction is, we have the beam coming out of the screen toward us, and we're essentially standing in front of the phased array and panel. Now, so I'm going to sweep the beam horizontally. Let me turn it down so you can get a better picture of this. Turn it down 90 degrees, so I'm essentially looking down on the top of the phased array, with the phased array going from left to right. Zoom in just a bit. Okay, I'm going to sweep the beam angle here. Sweeping it horizontally now. See the beam starts to sort of fall apart there, I guess. I'll take that as a limit. And looks like we have a sweep angle of 42 degrees from center. Again, the gain is held at 14 dB, and using isotropic point sources, what's interesting is you do see the power of the swept beam doesn't change. So I'm going to sweep it back to the other side horizontally, and you have roughly 42 degrees as well. Okay, so horizontally, the sweep is 82 degrees, total sweep, 42 degrees from side to side horizontally, and this is using no, with each element is exactly the same gain. Okay, and spacing is now lambda over 2. Okay, so let me go and reset everything, and let's look at the vertical sweep. Okay, I'm going to turn the beam to one side here so you can see a better angle of the vertical sweep here. Okay, so we're essentially standing on one side of the phase array, this being the front pointed out to the right, and our phase array is on its stand at the bottom, with the top of the phase array at the top of the screen. Okay, I'm going to sweep the beam vertically. Sweeping up, and you see it begins to kind of fall apart well, maybe there. See if we can get the okay, looks like that's roughly 40 degrees. Equivalent performance as essentially the same performance as the sweep from side to side horizontally. We see that same performance swept from vertically from top to bottom. Let me sweep it down. .40 degrees. Okay, so using isotropic point sources to illustrate the simulation package, we have a horizontal beam sweep of 84 degrees, vertical beam sweep of 84 degrees, with 5 point sources horizontal and 5 vertical rows. Our beam width at 3 dB down point is roughly 28 degrees. Total power of the beam is roughly 14 dBi. Okay, let me reset everything and give a final view of what this thing looks like. Okay, we're standing in front of the array now, and the beam is pointed out at us. So I'm sweeping it from side to side. And sweeping it up and down. We'll swing up and over. Okay. And now let's look at the possibility of changing the inner element spacing to see what impact that has. I'm going to reset everything back and turn the beam to one side here. Right now, inner element spacing is at lambda over 2. I'm going to decrease that spacing. I'm now at 143 degrees. You can see that our side lobes become less in number. The beam width increases. Now it's pi over 4 or 90 degrees. And what's interesting is if you continue to bring this inner element spacing down to essentially 0 degrees, then what you get is, to verify the software is working this perfectly, is that you get essentially a radiation of a point source now with a gain of 13.9 or 14 dB. Let me increase the axis here. And you see that in all directions. So it's like a super, this is essentially taking 25 point sources and stacking them all on top of each other to give a super point source. Okay, let me move back to lambda over 2 spacing, and now let me increase that spacing. So I'm going out to 270 degrees. And as you move the elements further apart, you can see the beam width becomes narrower and narrower, but you have more side lobes. And in fact, at this point, I'm at 300 degrees spacing between the elements, the isotropic point elements. That's your pattern. Okay. All right. This includes the first video. The second video will show the same phased array using the actual radiation pattern for the patch element from LCOM.